This video is about special cases of factoring. I know we've been doing factoring by grouping for a while, so let's take a look at kind of some special cases of factoring that are super handy to know. I'm going to start off by looking at these examples. All right. So x times x, that'll be x squared. X times 3 will be plus 3x. Negative 3 times x will be minus 3x. And then negative 3 times 3 will be negative 9. If we look at our terms here in the middle, the plus 3x, the minus 3x, they cancel themselves out. So we end up with x squared minus 9 as our solution. Let's see if the same kind of behavior happens in the next problem. 5 times 5, that's going to be 25. 5 times x will be plus 5x. Negative x times 5 will be negative 5x. And then negative x times positive x will be negative x squared. Our two terms in the middle, again, seem to cancel each other out, and we end up with 25 minus x squared. Interesting pattern. So I want you to take a second and think about what pattern these two problems are displaying. There is one, and it's got to do with that middle term. So what do you notice about that middle term? It kind of disappears, doesn't it? It cancels itself out. And that's kind of what is key about this. So let's do another example, just to, three's a charm. Make sure that this pattern continues to function the way we've seen it. So a times a would be a squared. A times 6 would be 6a. Negative 6 times a would be negative 6a. And negative 6 times 6 would be negative 36. Again, our middle terms are canceling out, and we end up with a squared minus 36. Easy enough. So what this is called is the difference of two squares. What we're looking at is an expression that is a squared minus b squared, and it factors into the two binomials, a plus b and a minus b. So let's see if these polynomials fit our pattern, right? So our first one here is x squared minus 9. X squared is a perfect square, okay. We've got a minus, good, and 9 is also a perfect square. So that one does definitely fit the pattern. Our next one, okay, 3. 3 is not a perfect square. That's not going to work. Even though we've got the x squared and the minus and the 16, that 3 breaks it for us. Our last one here, 25 plus a squared. 25 is a perfect square. Cool. Plus. Plus isn't going to work. It's got to be a minus. So for an algebraic expression to be the difference of squares, the first and last, let's say second, this is only 2, terms must be perfect squares. And the two perfect squares must be subtracted. I don't think I can fit that on there. All right, so let's look at this. You'll see how easy this is. It is short, sweet, and hard to beat. What I'm going to look at is, all right, my first term, what's a square root, basically, of 9? 3. Square root of x squared, x. We've got the minus, so it's going to be one of these, right? And then the square root of 49 is 7. Bam. These are nice and quick to factor. Okay, example number 2, square root of 16 is going to be 4. Square root of m squared will just be m. So we'll do plus m and then 4 minus m. Don't you love these? Okay, the last one looks a little different. Don't worry about it. Square root of 25 is 5. Square root of 4 is 2. Square root of x to the 4th is x squared. And the second term is the same thing, just with a minus. That's it. Not too bad, huh? We're going to look at a different case now. And as you can see here, it's got to do with this exponent. So let's go ahead and check that out. these behave a certain way, and let's see what they do. Now, I have noticed that a lot of you guys, when you're factoring, do tend to mess these up by distributing this exponent. That's not how distribution works. This exponent is saying how many times we're multiplying something. So just to write it out for you, that would be x plus 4 times x plus 4. Don't let that squared throw you off. So x times x would be x squared. X times 4 would be plus 4x. 4 times x would be plus 4x. And then 4 times 4 would be plus 16. And we end up with x squared plus 8x plus 16. And you can see this behaves significantly different than the other version did. And it also behaves significantly different than if we tried to just distribute this squared. We would get x squared plus 16. That doesn't work. We'd be missing the middle term. Let's try it again on this other one. I'm going to go ahead and write it out again. 3x minus 1 times 3x minus 1. So 3x times 3x would be 9x squared. 3x times negative 1 would be negative 3x. Negative 1 times 3x would be negative 3x. And negative 1 times negative 1 would be plus 1. And so when we put everything together, that's 9x squared minus 6x plus 1. And as you can see, this does not work the way you would necessarily think it does. 3 squared, okay, so that's 9x squared, and then minus 1, or plus 1, again, we'd be missing the middle term. So be careful to not distribute. This is multiplying. All right, so what did we notice? There's something a little bit different here, right? So look at our first term, our last term, and then look at that middle term. Something's kind of fishy here. So let's look at the next example. Again, I'm going to go ahead and write out what the problem is so we don't get confused. X times x is x squared. X times 3 is 3x. 3 times x is 3x. 3 times x, and then 3 times 3 is going to be 9. So we get x squared plus 6x plus 9. See the pattern yet? Okay, this is called a perfect square trinomial. And these are a little bit different, but they're really not too bad. So if you hadn't noticed, the first term is squared, just like you would think it would be. And the last term is squared, just like you would think it would be. And the middle part is what gets people confused. It's 2 times a times b. Or if it's a minus in here, it's negative 2ab. So these are actually pretty easy to factor. I'm not going to fill out this. Determine if polynomial perfect square trinomial. The first and last terms must be perfect squares. And the middle term will be 2 times the product of the first and last term square root. So let's see if we can't do this on example number D here. So can we factor this? Okay. A squared. So let's take a look here. Lost it on my tablet. There it is. Okay, so the square root of 16, that's going to be 4, right? So we have 4y as our first term. Now the question is, what's going to be b? And it looks to me like b, the last term, right? The square root of the last term is going to be 1. It's legitimately that hard. Now let's take a look at another example here. So we got our first and our last, all right? My guess is it's going to look like this. X plus 6 squared. Let's double check our work. So that matches and that matches. So 2 times a times b, so 2 times 1 times 6, that's 12, checks out. Let's look at number 5 here. So if we are to assume that this is a perfect square trinomial, then let's see, a square root of 9x to the 4th would be 3x squared for our first term, and our last term would be minus 5, and this would be squared. So that's our theory. Let's double check. Okay, 3 times 3 is 9. That works. X squared times x squared, that works. Negative 5 times negative 5, positive 25. That works. All right. So now it's 2 times a times b. So 3 times 5 is negative 15 times 2, negative 30. That is the correct factoring. That's how hard these are. You get better at spotting them the more you do this, I promise. So let's look at some kind of mixed practice here with some bigger numbers. Hopefully they won't freak you out too much. So number 6, I'm looking at this, and in my head I'm thinking, our first term's a perfect square. Our last term's a perfect square. This is probably a difference of 2 squares. Look, we got a minus in the middle. So that's literally all we're going to do. The square root of 81 will be 9. Easy enough. The square root of x to the 6th power would be x cubed. So we're going to have like this. And the square root of 100 is 10. Quick and easy. Let's look at number 7. This looks like a difference of 2, or a perfect square trinomial. We've got a perfect square at the beginning, a perfect square at the end. So we're going to try to factor this using that method and see if that works out for us. So let's see, the square root of 49, that's going to be 7, and then x. This has got a minus in the middle, so this will be a minus. And the square root of 1 is 1. Let's see if that is correct. 7 squared, 49. X squared. Negative 1 squared is positive 1. 2 times a times b. So 7 times negative 1 is negative 7. Times 2, negative 14. Checks out. So if you understand these special factoring cases, you can see that the factoring goes a lot faster than something like factoring by grouping.